Hi guys. So let's get started. Can you guys see my screen? Okay, thanks. Um, again, just a reminder, homework 4 is due tonight, and then next two homework assignments are already up online. Okay, so if you are ahead of time, you can go ahead and get them started. So today we'll be looking at chapter 6. This is the application of Newton's law. So it's basically the continuance of the chapter 5. Okay, so the first thing in this chapter talks about, actually it lays out the problem solving strategies for using Newton's laws here. So I just put it on the screen here. So the first step, as always, you want to identify the physical principles involved. Okay, and um, you will be also like listing the givens and then quantities to be calculated. Okay, so identify what are given and then what's asked to be calculated. Also, in the same time, you can probably get a pattern like information about something that it's not directly stated in the problem, but it's actually can be inferred from the problem. Okay, so and then also the second step is to sketch this situation using arrows to represent all forces. Okay, so this is preferring to you can just come up a very simple sketch to represent the problem. Okay, so as it says, a picture was 1,000 words, so that will help you understand the scenario. Okay, um, and the third step here is to determine your system of interest. So sometimes in a problem there are many objects in the problem, but in order to figure out what's asked, you might not or you probably not have to consider all the objects in some scenarios. Okay, so maybe just isolate one or two of the object that should be sufficient enough to solve the problem. So once you have identified your system or object of interest, then draw the free body diagram on the objects, okay, or the system. Then the next step is apply Newton's second law to solve the problem, okay? And if necessary, you will have to use the kinematic equations from the chapters before, in addition to the Newton's second law, okay? And then at the last step is what we usually have for all other problems. You want to check to see if your answers make sense or not, okay? By using some common sense or simple estimation. All right, so um, so last time we kind of talked about like when two objects has in contact. So we look at or maybe the time before, I don't quite remember. When we look at two boxes in contact, so I believe it was like 2 lectures ago. When we look at two boxes in contact, okay, so then they share the same oscillation and motion. So in that case, you can treat them as one system. Now, a lot of times, two objects, they can be connected like with a string or rope, like in the figure shows here. So these two boxes are connected with the string. And then when string is involved, oftentimes you'll find a pulley in the system as well. Okay, so then these two are connected. Now, they do not necessarily share the same oscillation because oscillation is a vector, but they may share the same magnitude of oscillation, right? Because direction of the oscillation for these two boxes, they are different. So one is in the horizontal direction, one is in the vertical direction, but their magnitude will be the same because they are connected, okay? So then their speed could be the same as well, okay? Although the velocities are not the same, okay? So when you have object that is connected with a string or wire or rope, etc., they are called connected bodies, okay? So in this scenario, because of factor that you have a pulley involved, so then the tension in the string here actually will be pointing at different directions, okay, because of the pulley, because pulley, as an ideal pulley changes the direction of the tension. So in that case, you can actually set up separate coordinates for the two objects here. So on the table, the box one on the table here, you can set up the X to be along the table surface and then Y to be perpendicular to it, okay? Now for this guy, for this box two, you can set up the X is along the vertical direction going downward, okay? And then Y is going in that direction, okay? So you have separate coordinate system for separate objects, okay? So that's fine, because when you are looking at the components, X and Y components of the motion for each of the objects, okay? So then you are pretty much focusing on the scale quantity of the velocity and acceleration, etc. So in that case, the direction doesn't really matter, okay? So the only thing matters is the magnitude in that case, okay? So if you set it up that way, then X direction for this box, okay? And the box is moving in the X direction for box one, then box two is also moving in the X direction, okay? But in its own coordinate system. So we will take a look how a problem can be solved. So today we are going to just look at a couple of problem solvings here for the class. All right. So let's look at the first one here. So this one says you have two blocks connected by a string as shown in the figure here. The smooth inclined surface makes an angle of 42 degrees with the horizontal, and the block on the incline has a mass of 6.7 kilograms. Find the mass of the hanging block that will cause the system to be in equilibrium. Okay, so when it says the system is in equilibrium, that means it's not it's either not moving or moving with a constant velocity. Okay, so let's just say it's not moving. Okay, in this case, because in both scenarios, if they are in equilibrium, then the net force should be equal to zero each of the objects. Okay. So I'm gonna to give you guys a few minutes to try to see if you can solve all this by yourself, and then we can like take a look at the solution together. Okay, you can submit your answer by clicking on the problem here. It will give direct you to a page where you can submit your response. Okay. Oops. All right. Okay, so let's take a look here. So we are asked for um, M. So what's this M, right? So we probably can start with looking at this block here because we are looking for its mass. So um, so the first thing, this might be our the first thing to look at is this guy. This is our object of interest here. So now let's look at the free body diagram on this guy. So the first thing, the first force you want to draw is the gravitational force or the weight, right? So because we are near the surface of Earth, and then the second force on this guy should be the tension because the tension is holding it upward here. So this is tension force, okay? So you can see from this free body diagram for the hanging mass, okay? For the hanging block, um, this looks like tension is going to be equal to mg because if this is in equilibrium, then these two should cancel out, right? So T will be in equal to mg. So this is what you can get from the free body diagram. You can do the same as what we did earlier. You can write that net force is equal to tension minus mg. Okay, and then because it's in equilibrium, so then net force will be equal to 0. You set this two up, right? Then it tells you T minus mg will be equal to 0. Or if you are familiar with this procedure by now, then you can directly write it out that T is equal to mg by just looking at the free body diagram and then noticing it's in equilibrium. So then T should be equal to mg. Okay. Um, so this is what we have now, but because there's a string here going through the pulley here, so you can set up the X, all right, to be in this direction and Y to be in this direction. Or you can start with this on this block here for the coordinate system. You can say, I want to set up X to be along the surface and then Y to be perpendicular to the surface for this block on the incline surface. Now, the key to set up the XY coordinates for the other block is you just move this X and Y coordinate system along the direction of the stream or the rope, whatever it is. Okay, so you're going to just move this guy, keep this X, okay, in the direction of the rope here, and then move it all down here. All right, so then this is the X for this guy, and then this is the Y, okay? So you want to keep the axis, that one axis that is the same in the direction of the motion if the object will be moving, okay? But now in this case, it's not moving, so you can kind of imagine if this is moving along the surface, then it will go in that direction, right? So move the X axis along the stream direction, and then will be this guy here, okay? Pointing downward to be that one. All right. So then it looks like if you are looking for m here, now you get this relationship of t equal to mg. So then you can do t divided by g, but the problem is we do not know the t, right? So now you have two objects in the system. If you don't know t from looking at one object, then you probably can turn to the other object because these two are connected, right? So then you'll be looking at this guy here, this object on the inclined surface here. You want to draw its free body diagram. So again, the first thing will be the weight. Okay, I'm just going to call this bigger, capital M, okay, for its mass. Because it looks like this guy is probably going to be heavier than this one. Okay, so if this one is small m, I can use bigger m, or you can say m1 on the surface, m2 to be the hanging mass. So whatever. Now, because this block is on the surface, so you can indicate there's a normal force by contact, okay? That should be going in that way. There should be this tension because it's being pulled by the string here, so this tension here, all right? So because there's this pulley, so then tension here and then here should have the same magnitude. Okay, although they are pointing in different directions, but they should have the same magnitude. So then to solve for M, you need T. So then we can probably figure out T by looking at the free body diagram of this guy. Okay. So this guy, because now you have X and Y in that X along the surface, Y perpendicular to the surface. So then these two are already either in the X direction or Y in direction. So then you just have to resolve the weight into the X and Y component. Okay, so this is the X component of the weight, and then this is the normal component of the weight. Okay, so from last time you probably can figure that now for the X direction should be mg sine because you are on an inclined surface. For the Y component should be mg cosine. Okay. So if you resolve that, then you can cross that original weight out. So then for the block on the inclined surface, all right, you can say its net force in X direction should be T minus capital M G sine theta, right? And then its Y direction should be normal force minus capital M G cosine theta, all right? But the system is in equilibrium, so that means net force is equal to 0 in X direction. Net force is also equal to 0 in Y direction. Okay. Again, you get this set of equation from the free body diagram, right? And then you get this set of equation from the second law, Newton's second law of motion, right? So then you can set the two equal to each other from the right hand side of equation. Okay, so this guy should be equal to that guy. So T minus capital mg sine of theta should be equal to 0. All right. So then, because you know capital M, that's given, G and then theta, it's also given. So you should be able to solve for T now. So T is equal to capital G sine of theta. Okay. Now, looking back here, small m times G is equal to T. So then this is equal to so capital G sine theta is equal to small m times G. Okay. So you'll see your G and G will cancel out. All right. Your small m should be equal to capital M times sine of theta. Okay. So then you can plug in your numbers now. Sine of 42 degrees, that would be equal to 4.48 kilograms, all right, or 4.5 kilograms. Okay, so this is your small m. All right. Any questions you guys might have? You can unmute yourself and speak up. Okay. All right, and then I think yeah, the responses I got for most of you guys, you got 4.5 or 4.48. Okay, so and it looks like there's one 4.98. I'm suspecting there might be a typo there. Okay. All right. Okay, so that's the first one here. Now let's move on to the next one. Again, this is a connected body here. All right, two are connected together through a rope here. So it says the 3.5 block is on the smooth tabletop. Again, when you see smooth, that means there's no friction. Okay, and then it's attached by a string to a hanging block of 2.80 kilogram, showing in the figure. The blocks are released from rest and allowed to move freely. Is the tension in the string greater than, less than, or equal to the weight of the hanging mass? B, find the acceleration of the blocks, and then C, find the tension in the string. Okay. I'll have you guys again try to work on this, and then in a few minutes we can take a look at the solution together. Okay, and once you have your answer, you can click on the problem here to submit your response. I think I'm gonna to give you guys a couple more minutes to work on this one. And then if you have finished this one, you can take a look on the next problem and then see if you can come up with a plan, okay? But in 2 minutes, we'll be looking at the solution for this one together. All right, so let's take a look on here together. So I'm looking at your responses here. Most of you guys says A is tension is equal to the weight. Okay, so let's take a look. So on my paper here, I have the two boxes drawn here. So now we'll take a look on the box one by one. Okay, so let's take a look at the free body diagrams of them. So the first one here, you can imagine there should be a weight of mg. So let me call that as m1g because there are two masses here. So you want to distinguish between the two. And then there's this normal force, supporting force to that one. Okay, so these two should cancel out, right? Because the block is moving along the surface, not in the vertical direction. So these two should cancel out. This guy is pulling it, so there should be tension on it, right? So this is what you should have block one on the table here, okay? Because it says it's a smooth table, so there shouldn't be friction force here. So looks like there are three forces here, two of them cancel out, so then the resultant should be this guy, okay? So let's use the x along the surface of the table and then y perpendicular to it, all right? Now we can move this coordinate system along the stream direction here and then move it down here. So then on this hanging block here, you will have x in the vertical direction, you will have y in that direction, okay? So moving over here, on this guy here, you again, for the free body diagram, you would expect there's weight of the block, M2G, it's a hanging block, so let me call it M2. Now there's tension, right? Okay, so let's imagine what will happen if you let go of the two blocks. Okay, so it looks like if you let go of the two blocks, this guy is going to move down, right? And then this guy will be moving in that direction, right? So there will be velocity and acceleration in that direction, right? Because initially, if you are holding this hanging block, then they can be in equilibrium. But once you remove or let it go, then you will start to move. The whole system will start to move. So the block on the table will be going in this direction. This guy will be going in that direction, right? So there's a change in velocity. So then that means there should be acceleration, right? So now in that scenario, if you look at the free body diagram for the hanging mass over here, so then for hanging mass, you can kind of look at the free body diagram here, right? So then the net force, if you specify in the vertical direction, which is its x direction, then should be the m2g minus t, right? And then in y direction, there's no motion, so we don't have to care about y direction net force, okay? Or there's no force in y direction, you don't have to care about that. Also, so this is again from free body diagram. From second law, you can say net force in x direction is equal to mass times acceleration in x direction, right? Now in y direction, there's no acceleration, so I'm going to just say m times a, okay, without having the sub x. So in this case, it looks like because you have changing in velocity, so this guy is not zero, right? So then this should be equal to this guy. So m2g minus t is going to be equal to ma, right? Which a is not zero, so that means this is greater than zero, right? Because it's going down in the positive direction, okay? So then it should tell you m2g minus t is greater than zero. So m2g then should be greater than t, okay? So this is what you should have for part A. So I see most of you guys didn't get this right? So yeah, so now you can see because it will stop moving downward, we'll have an acceleration on it. So then T shouldn't be equal to m2g. Okay, so T is not equal to the weight. All right. So the tension should be less than the weight in this case. Okay, the weight is greater than tension, so then tension is less than the weight. Okay, it equals to the weight when you are holding the blocks so they are in equilibrium. Okay. I'm actually glad that you guys didn't do this right now instead of in the test. Okay, so now when the test comes, you'll know that what's right. All right, so B is asking you to find the acceleration of the blocks. Okay, so you probably can realize because these two are connected together, and they will share the same acceleration, the magnitude wise. Okay, so the direction wise they are not the same, but magnitude wise they should be the same because they are connected, right? How much this one is moved, then if this one is moved by amount, say 5 meters, then this one should be also moved by 5 meters in the same time. Okay, so velocity will be the same. The change in velocity should be all the same because they are connected. Okay, so they will share the same acceleration in magnitude. Okay, so we can take a look. The hanging block here, we have this equation, right? When we look at the free body diagram and the second law of motion. So let's take a equation down here. So m2g minus t equals to m2a. Sorry about that. I should have m2 there or m2 here. Okay, because that's on the hanging mat. So m2 here, m2 here. Okay, so this is from the hanging block. All right. Now let's look at the block on the table. All right, so its net force should be just this T, right? Because these two cancel out. So net force is equal to the T, right? So this is again from free body diagram. And then from the second law, you can say net force is equal to M1 times A, right? So the net force should be equal to the mass times its acceleration. So this is from the second law. All right. So combine these two, you can write that T is equal to M1 times A, right? So now you have this equation. You have first equation, you have second equation, okay? By looking at the free body diagram and applying Newton's second law of motion for the two. All right, so now in these two equations, for the first equation, M2 is given, G is the constant, T is not, right? M2 is given, A is not. So two unknowns here. On the second equation, you also have two unknowns, okay? So then combine the two equations, you should be able to solve for both, okay? Both the tension and then acceleration. So you can find the acceleration for B and then find the tension for C by looking at this equation together, okay? So so when you have two equations and then two unknowns to solve, okay, let me rewrite it somewhere here. So m2g minus t equals to m2a, and then t equals to m1a. So these are the two equations we'll be looking at, and then the two unknowns will be solving is t and a. Okay. All right. So we say if you have two unknowns and then with two equations, so you can start from one equation, write one unknown in terms of the other unknown, and then plug the expression into the other equation, right, to solve for the unknown. Quick example on the two equation, you realize the second equation already have the unknown, one unknown expressed in terms of the other unknown. So then you can just replace this expression into the first, okay? So replace t equal to m1 times a in the first equation there. So then m2g minus m1a equals to m2a, right? So then you are looking for a is the unknown. You move m1a to the other side of the equation, m2g equals to m1a plus m2a, all right? And then single out the a, or factor a out. So m1 plus m2 times a will be equal to m2g, okay? Now to solve for a, you divide both sides by m1 plus m2, right? m1 plus m2. So your isolation then equals to m2g over m1 plus m2, okay? m2 is 2.8 kilograms times 9.8 meters per second squared, divided by m1 is 3.5 kilograms plus 2.8 kilograms, okay? So plugging the all you have into your equation, you will get 4.356 meters per second square, okay, or 4.36 meters per second square. All right, so this is your acceleration. Now once you have found your acceleration, take the acceleration into the second equation here. You can calculate for your tension, okay? So your tension for C is equal to m1 times acceleration, so 3.5 times 4.356 meters per second square, okay? That will be 15.2 newtons, okay? I saw several of you guys got the B and C right, but didn't get the A right, okay? So in A, you should have the tension less than the weight, so then the system will have oscillation, okay? Questions you guys might have? All right, so if not, then we'll look at the next one here, next example here. So this one is about Newton's laws and kinematics, okay? So far when we talk about free body diagram and then second law, application of second law, we rarely use combination of the second law with kinematics, but this one, it's kind of revisit. I think we talked one or two examples before when we check on Newton's second law, but let's take a look on this one to see, again, the combination of second law or Newton's law of motion and then kinematics, okay? So this one says a basket player jumps straight up for a ball. To do this, he lowers his body 0.300 meters and then accelerates through this distance by forcefully straightening his legs. This player leaves the floor with a vertical velocity sufficient to carry him 0.900 meters above the floor. calculate his velocity when he leaves the floor. Okay. And then B, calculate his acceleration while he's straightening his legs. How he goes from 0 to velocity found in A in a distance of 0.300 meters. Okay. C is asking you to calculate the force he exerts on the floor to do this, given that his mass is 110.0 kilograms. Have you guys tried this one out first? Okay. And then if you have your answers, you can click on the problem to submit your response. So when you sketch the situation here, I think it's easier if you just use a point to represent his body. Okay. So for example, when he straightens his leg, the body moves by 0.300 meters. You can just use a dot that moves by 0.300 to represent the scenario. Okay. So then this one will be very similar to the one you did in your test. When a ball is dropped from a certain height and then it hits the floor and then bounces back. All right, I think I saw a couple of responses in here already. So if you did submit your responses A and B, those two have agreement on A and B, but not C. So the second response is the correct one. On the first one, on C, you probably didn't include the weight of the body itself, of the body, the player itself, okay? So check on that one. But I think we are just going to stop here for today. If you haven't finished your, on this one, you can do it up to the class, but we are going to come back tomorrow and then to check on the solution together, okay? I don't think we have enough time to go through the full solutions here today, so we'll just stop here for today. All right, I'll see you guys tomorrow, okay? You guys, bye.